Welcome to this lecture. This is the first lecture of week 6. In this week, we will start with discussing a new type of convergence for random variables. This type of convergence will be through the associated distribution functions. So, without further delay, let us start recalling the basic concepts involving the underlying probability law of a random variable and the corresponding distribution functions. So, we move on to the lecture slides. So, we start with this basic recall of the connection between random variables, probability measures and corresponding distribution functions. To start off with, let us say mu is a probability measure on the real line on the Borel sigma field. Then we can look at the corresponding distribution function defined this way, that for any real number x, look at the size or the probability associated to the interval minus infinity to closed small x. So, that value we associate to this function, and that is how we end up with the distribution function corresponding to this measure mu. On the other hand, remember that given such appropriate distribution functions which are non-decreasing right continuous and has limit 0 at minus infinity and has limit plus 1 at plus infinity, then corresponding to that we can also construct probability measures. So, that is coming from the correspondence between probability measures and corresponding distribution functions, and this same correspondence essentially gets extended to the case of random variables. So, again let us set up the notations. So, if you have a random variable x defined on a probability space omega f p, we can look at the corresponding law which we denote by p compose x inverse, and this is a probability measure on the real line once more. And therefore, exactly as discussed above, we can look at the corresponding distribution function which we now denote by f subscript x, just to denote that it is linked with the random variable x. So, what we do is that we simply look at the value of this. So, for any real number small x, look at the interval minus infinity to closed x and look at the size associated to that interval by the probability measure p compose x inverse, and that is what is giving us the distribution function's value. And of course, a simplified notation that we have also discussed earlier is the probability that the random variable takes value less or equal to small x. This is coming from our earlier understanding that this pre-image that we have used in the previous step, that can be thought of in this explicit way, that it is all points on the domain omega such that the random variable takes the value less or equal to small x. And what we simply do is that we get rid of this small omegas everywhere, and therefore, we end up with this simplified expression that is also connected with our understanding of distribution functions of random variables as we study in the basic probability theory. Alright. So, again the idea is, if you know the distribution function of a random variable, then you can construct the probability law of the random variable, and if required we can construct explicit functions capital X such that the probability law is exactly given by that coming from the distribution function. So, in principle, if we know the distribution function, we know completely the law of the random variable. Now, what we are going to focus on are certain results involving distribution functions, and here we are going to focus on distribution functions corresponding to random variables, and in some cases for distribution functions corresponding to probability measures. But as we have already pointed out, there is this nice correspondence between random variables and their probability law. We can work with any kind of distribution functions in either setting, meaning the distribution functions may correspond to either random variables or the distribution functions are actually coming through certain probability measures. In either cases, what we are going to do is that we simply call them as distribution functions, and we can always go back to specifying the either case if necessary, meaning we are going to state results for distribution functions, but these results will be applicable to distribution functions for random variables or distribution functions coming from probability measures. So, with this starting point, let us first recall this necessary structure of a distribution function. So, again a distribution function on the real line has this following characterizing properties, that it should be non-decreasing, right continuous, and the limit at infinity should be 1, limit at minus infinity should be 0. And typically we shall denote the limit at infinity by the notation f infinity and the limit at minus infinity by the notation f at minus infinity. Alright. So, these three properties, meaning non-decreasing, right continuous, and the appropriate values of the limit at plus and minus infinity completely characterizes a distribution function. Meaning, if you have any such function satisfying these three properties, we can construct the corresponding probability measure and therefore construct a random variable with this function as the distribution function. So, with this recall, what we are going to focus on are convergence of random variables, and the idea is that we are going to focus on the convergence of the corresponding distribution functions, and it seems reasonable to attempt to make such a mode of convergence meaningful through the convergence of the distribution functions. So, now we first start by looking at some necessary properties of the limit of sequence of distribution functions, meaning I will now look at a sequence of distribution functions coming from either a sequence of probability measures or a sequence of random variables, and then what we are going to assume is that the pointwise limit for the sequence of distribution functions exist, and look at the corresponding properties of this limit function. So, that is what we are attempting to do in the next result. So, let us see. So, here we are starting by setting up the notation that we are having this sequence of distribution functions denoted by Fn. Now, suppose that for all real numbers small x, if I look at the limit of this Fn x as n goes to infinity, this should converge. So, that is the assumption, that is the hypothesis of this result, and we denote that quantity, that limit, as f of x. So, therefore, we end up with a limit function which is associating the value of this limit to all points small x. Alright. So, let us now focus on the properties of this limit function capital F. So, what we claim is that capital F takes values between 0 and 1, and moreover it should be non-decreasing. So, let us see a quick proof of this. Proving this is straightforward. So, the first thing we observe is that since Fn's are given to be distribution functions, they take values between 0 and 1. So, therefore, as n goes to infinity, the limits will also take values between 0 and 1. So, therefore, the part 1, that the limit function capital F takes values between 0 and 1 follows immediately. And let us now look at the non-decreasing property of the limit function capital F. So, to do that, we start with any 2 points small x less than y. Now, again go back to the individual distribution functions. In the Fn's, we have the non-decreasing property. So, therefore, as soon as x is less than y, we will immediately have the values of the distribution function Fn at x will be less or equal to the value at small y, and this is true for any n, because for each n we have assumed Fn to be a distribution function. Now, if you take limits on this relation here, as n goes to infinity, we will end up with the relation that f of x is less or equal to f of y, because that is exactly are the values of the limit, and therefore, we immediately get back the non-decreasing property of the limit function capital F, and part 2 follows. So, the proofs of these two properties for the limit functions are immediate. However, let us recall again, for a distribution function we must have 3 important properties: non-decreasing, right continuous, and the limits at plus and minus infinity should be between 0 and 1. Now, for the limit function of a sequence of distribution functions, we have managed to ensure the non-decreasingness of the function, and we also have that the function takes values between 0 and 1. But we are interested in the other 2 properties, which is right continuity and the appropriate limits at plus and minus infinity. Let us see. These appropriate limits at plus and minus infinity and the right continuity, actually these 2 properties may not hold for this pointwise limit function of our distribution functions. And to show this, what we do is that we consider some explicit examples. So, let us start with a sequence of random variables xn, where we consider the nth random variable xn to be degenerate at the number 1 by n. Alright. So, if I take positive integer small n, let us say equal to 1, then I am taking x1 to be degenerate at 1. For n equal to 2, I am saying x2 is degenerate at half. Now so on, if we look at the sequence of random variables defined in this way, that we can look at the corresponding distribution functions. Now again, if my small x is strictly less than 1 by n, then the corresponding probability which is getting found out or written by the distribution function is actually 0. If small x is greater or equal to 1 by n, then the corresponding value is 1. So that is the distribution function corresponding to this degenerate random variable xn. Now if we look at the pointwise limit function corresponding to this sequence of distribution functions, we will end up with this fact that as long as my small x is less or equal to 0, the limit function takes the value 0. If x takes positive values, then the corresponding limit function takes the value 1. To say this, it is immediate that as x is less than 0, then it is immediate that all the fn x are all equal to 0. So therefore that limit is 0, that is verified. Now let us say I look at the case when x is also equal to 0. In this case also, if we go back to the values of fn of x, so fn of 0 is what we are looking at now. If x equals to 0, then that value is also 0. So therefore we have verified the value 0 for this first case. Now if x is strictly greater than 0, in this other case what we observe now is that there exists a large enough positive integer capital N such that this will give us that x is therefore greater than 1 by n. So for large enough capital N, then for all small n greater or equals to capital N, my x will be greater than 1 by small n, and hence as a consequence fn of x is 1 for all terms starting with capital N, and therefore the limit of fn x as we are looking at here is 1. So that is the so these probabilities are 1, this is 1, so therefore this limit is 1 as written here. Alright, so here just to simplify the notations I am writing fn x, but we are actually looking at f of xn. Alright, so these limits that we are considering, we have figured out the exact values over the whole real line, that is giving us this limit function. But note that if we look at the right continuity property of this limit function capital F at 0, that this right continuity does not hold, because if we approximate the point 0 from the right, then for all those points the limit function takes the value 1. So therefore the right limit at 0 for the limit function capital F is 1. We are going to write that fact writing like this, that the right limit at 0 for the limit function capital F is equal to 1. However, this is not equal to the value 0, which is the value of f of 0. Alright, so therefore we do not have the right continuity property of this limit function capital F. We are also going to show some other examples where the appropriate limits at plus and minus infinity does not hold for the limit function. So here what we start off with are again another sequence of random variables, but here for each n this is distributed uniformly over the interval minus n to plus n. Now here the corresponding distribution functions again can be written very explicitly, that if x is strictly less than minus n, then the value is 0. If x is greater or equals to n, then the value is 1, and in between this range you can figure out that this is exactly the uniform distribution function. Alright, so here we are considering the uniform distribution over minus n to plus n. So that is what it is. So now if you let n go to infinity and look at the limit function, then you can immediately compute that the limit function takes the value of for all values of small x. So therefore in particular this limit function is a nice function, it is a continuous function throughout the real line, but it is also a constant function, and therefore if we look at the limit of this limit function at plus infinity and minus infinity, both turn out to be half, and in this case this does not match with our expected numbers, which is the limit being 0 at minus infinity and limit being 1 at plus infinity. So what we have managed to show in this example is that for the limit function of a sequence of distribution functions, the limit at plus and minus infinity, the correct values may not hold. Alright, so we will see another example of this type. So, suppose I look at again another sequence of random variables where the nth random variable xn is degenerate at the positive integer n. Now, here again we are going to write down the distribution functions. So, if x is less than n, the value is 0, if x is greater or equals to n, the value is 1. So, again as computed earlier, you can try to compute the limit function here, and we are able to figure out that the pointwise limit actually turns out to be identically 0, meaning for all small x the limit function takes the value 0. Now, here you note that the limit of this limit function at plus infinity is 0. So, therefore, this also does not match with the expected number plus 1, which should be the appropriate limit at plus infinity. Alright. So, essentially what we have ended up observing is that if we look at a sequence of distribution functions which we assume to converge pointwise, then the limit function need not be right continuous and need not have the appropriate limits at plus and minus infinity. But now what we are going to do is that we are going to relax the type of convergence that we ask for the sequence of distribution functions that we are considering now. So, the relaxation has to be done in a systematic manner, and to do this we are going to look at this next result, and this next result is going to help us say that we have to look at the limit function not at all points, but with certain special points small x on the real line, and this result is typically referred to as the Helly's selection theorem. So, to start off with, we assume that we are having a sequence of distribution functions, and a priori I do not make any assumption about the pointwise convergence of this sequence of distribution functions. But the theorem states that we can extract a subsequence which we denote by f and k of this sequence of distribution functions such that you can also figure out a non-decreasing right continuous function f such that the expected limit holds, but only at the points where the limit function capital F is continuous. Alright. So, again the theorem says that we can construct two things. First, we can construct a function f on the real line which is non-decreasing and right continuous. So, these two properties must hold for this function, and secondly we can construct a subsequence of the given sequence of distribution functions such that this subsequence converges to the function capital F, but only at the point small x where this function capital F is continuous. Alright. So, that is the statement of the theorem. Now, before proving this, let us see some important consequences of this theorem. So, the first thing is that we are going to see the construction of the function that we do in this theorem that will satisfy the property this function capital F takes values between 0 and 1 as we expect. However, the appropriate limits at plus and minus infinity need not hold. So, just to be clear, we have ensured that we can figure out a subsequence of the distribution functions which converges in a certain sense to a limit function capital F, and this limit function capital F is non-decreasing and right continuous, but we cannot ensure that the correct limits holds at plus and minus infinity, and therefore what we conclude is that the limit function capital F that we have thus constructed need not be a distribution function. So, to ensure or to convince ourselves that for the limit function capital F the correct limit does not hold, we just have to go back to the examples 2 and 3. Alright. So, if you go back to those examples, we can show that the corresponding function which is continuous, then for such a function the appropriate limits at plus and minus infinity does not hold. So, again the limit function we have still not been able to ensure that this is a distribution function. But now, motivated by this theorem, what we are going to focus on are the continuity points of the limit function. So, by continuity points we simply mean the points on the real line where the limit function is continuous. So, at the continuity points we would like to ensure the corresponding convergence even if it is through a subsequence. And what we are going to do later on is to consider the convergence of distribution functions where we are asking for the convergence pointwise, but only at the continuity points of the limit function. And this notion or this idea is going to give us another mode of convergence of random variables, which we shall discuss in the next lecture. Okay. And finally, one other important observation is that we have already pointed out in part 1 of this remark that the limit function that we are looking at now need not be a distribution function, because the correct limits need not hold at plus and minus infinity. Now, to ensure that the limit function actually turns out to be distribution function, meaning it needs to satisfy those limits at plus and minus infinity, to ensure that we actually need to impose certain additional conditions, and these conditions will be put on the sequence of distribution functions that we consider, and these type of conditions will be discussed in a later lecture. Alright. So, let us come to the proof of Helly's selection theorem. So, this is using a very standard technique that we use in analysis. So, what we start with is we look at the set of rational numbers which is denoted by q. We know that this set of rational numbers is countable, and therefore, we can enumerate the rational according to the natural numbers, meaning we can consider a rational number R1, R2 and so on. So, all the rational numbers can be enumerated this way. Now, for any rational number smaller, what we observe is that if we just evaluate the sequence of distribution functions at that point smaller, that is going to give us a sequence of real numbers, and this sequence of real numbers is bounded between 0 and 1, because fn's are given to be distribution functions. So, therefore, their values at any point smaller is between 0 and 1. So, this is a bounded sequence and takes values between 0 and 1. Therefore, no matter which rational I consider, then we can always extract a convergent subsequence from this bounded sequence fn of r. Now, we apply this observation and do a certain kind of a construction. This is a construction that is typically referred to as the diagonal method. So, what we do is that we first look at the rational number R1. Then for this rational number R1, this sequence is a bounded sequence, and therefore, we can construct a or we can extract a convergent subsequence, which we denote using this new index m, and the subsequence is denoted with fn1 comma m. So, this 1 simply corresponds to the fact that we are looking at the first rational, and corresponding to the first rational we are just extracting a convergent subsequence. So, now here you see that this set of natural numbers which is giving us the subsequence, which is n subscript 1 comma m, that is a strictly increasing sequence of natural numbers. What we do now is that we are going to look at the second rational number R2, and corresponding to that we are going to look at the sequence with these specific indices coming from the first rational that we have considered. Now, here again this sequence is bounded between 0 and 1, and therefore, we can extract a further subsequence which we now denote by n2 subscript m corresponding to this R2, which also converges, alright, and therefore, this subsequence is also convergent, right. So, that is essentially the idea. So, once we construct this further convergent subsequence, note that with these new indices, which is a further subsequence, original R1 corresponding sequence also converges, because that is what we have already ensured, alright. So, if you look at these further subsequences at each r according to their enumeration, meaning next step we are going to look at the rational number R3, and we are going to construct a further subsequence fn subscript 3 comma m, which will ensure the corresponding convergences for R1, R2 and R3. So, if you repeat this, what we are going to look at is that at each step we are going to end up with a further subsequence which converges. Now, finally, we are going to look at what is known as the diagonal sequence given by f n comma m, and if we look at that by our construction, for any rational number small r, this sequence must converge, alright. So, please check this fact that if we look at now the diagonal sequence, then for each rational number it will correspond to certain enumeration, and therefore, we can ensure that for all such rational numbers these diagonal sequence must converge. And therefore, what we have ensured is that this limit holds for these diagonal sequence for each rational number smaller. So, we have ensured the existence of the pointwise limit, but only for the rational numbers, and to do this we have used the diagonal method. Now, for notational convenience, we are not going to write down this explicit expression of this limit for this specific subsequence, we simply denote it by g of r. This is just for notational convenience. So, now what we do is that using these values g of r, which are known for all rational numbers small r, we are going to define a function capital F explicitly in this way, that we take any real number small x and look at all rational numbers exceeding small x. Then look at all the values g of r and consider the infimum over all such numbers g of r, and whatever is that infimum we take this as the value of f x, alright, and this explicitly gives you a function on the real line which we denote by capital F. And for this function what we observe is that by construction itself this is non-decreasing. This is follows immediately by the construction, because if we look at any 2 points x greater than y, then the collection of rational numbers which exceed small y, they also exceed small x. So, if any rational number smaller exceeds small x, then it also exceeds small y, and therefore, considering the comparison between the type of numbers that we are considering here and the properties of the infimum, we end up with the non-decreasing property of capital F. Now, we are going to show the right continuity of the limit function capital F that we are using now. So, here let us fix a real number x, we want to check the right continuity. So, to do that let us fix a arbitrary epsilon positive, then for that epsilon positive, using the definition of the infimum which is used in the definition of the function capital F, then there exists this rational number r such that r exceeds small x and the value of g of r must be smaller than f of x plus epsilon. This is just following the definition of infimum. Then what we do is that we now look at all real numbers between x and r, x included, r excluded. Then for all such real number small y, we look at this quantity, that just by the non-decreasing property of capital F, the first inequality holds, but since y is strictly less than r, the second inequality essentially gives you that these rest of the inequalities hold, alright. So, this is just by the definition again. Therefore, we end up with this type of inequalities which compares the values of f of y against f of x and f of x plus epsilon, and consequently we have ended up with this estimate that f of y minus f of x, they essentially are close, and closeness is in the sense of epsilon, that it is still smaller than epsilon, this quantity. Therefore, we have ensured that f is right continuous because y is any arbitrary point we have chosen from the right neighborhood of the point small x, and this choice of small r was from the choice epsilon, and since epsilon is arbitrary, we have ensured that the right continuity holds. Now, finally, our interest is to ensure that at the continuity points of the function capital F, this limit holds. So, again these are the quantities that we are denoting by the function capital G, and we want to show that this limit holds for all continuity points small x of the limit function capital F. Here again, to ensure or to verify the limit, we again start by looking at some arbitrary epsilon positive. Then what we do, we fix a y strictly less than small x such that f of x minus epsilon is less than f of y. We can always ensure just by the properties of the function capital F. Now, here we are using the continuity of capital F at the point small x. Now, we can find a rational number small s greater than small x such that g of s is less than f of x plus epsilon. This is just by the definition of f of x through the infimum over this g of s. Alright, so we have this inequality. Then if we pick up another rational number between y and x, then immediately certain inequalities follow. So the first thing which we have already ensured, that f of x minus epsilon is less than f of y. So that we have already ensured. But since r is greater than y, we have ensured this inequality, and using the properties of the function g, we ensure that g of r is less equals to g of s, and finally we end up with the g of s is less than f of x plus epsilon, which we have also ensured. So combining everything together, we have certain inequalities involving these quantities. Now let us look at the sequence level relations. So if we look at the rational numbers r and s which are on either side of small x, we end up with these inequalities, and therefore by taking limits as m go to infinity, we end up with this fact that limit inferior of these bounded sequences is less equal to the limit superior of this bounded sequence. So that is automatically following. But from our earlier relation that we have ensured, that will tell you that the limit inferior must be greater or equals to f of x minus epsilon, and the limit superior must be less or equal to f of x plus epsilon. And since epsilon is arbitrary, we have ensured that first of all these limits essentially vary within the distance to epsilon. So therefore these two, limit inferior and limit superior, must match and give us the required existence of the limit. So the limit exists, and moreover it should match with f of x. So this completes the proof that at the continuity points of the limit function capital F, we have ensured the existence of the limit. Alright. So we have proved the Hellis selection theorem, and this is telling us that whenever we are looking at a sequence of distribution functions, if we want to look at the pointwise limit function, our interest should be to look at the continuity points of the limit function and then do the analysis. So in the next lecture, we are going to start off with a limit function which is a distribution function, and on the continuity points of this limit distribution function, we are going to ask for certain type of convergences, and that is going to give us a new mode of convergence for random variables. This is what we are going to discuss in the next lecture. We stop here. Thank you.